Another equation related to Young's experiment is that how we are going to find that vertical distance here. Can you see this one y1, this one y2? And we can actually here use simple trigonometry. This is y1, this is theta 1. The distance between the two slits and the screen, if we call it r, I'm calling it r, not x, okay? Then I'm gonna say tan theta is the opposite divided by the adjacent. When theta is very small, theta equals sine theta equals also tan theta. You can try it. Enter the I will say the angle to be 0.1 and see what is sine in radians, of course, what is sine theta and what is tan theta. Therefore, here I can replace tan theta with sine theta, and I know this is for constructive and this is for destructive. Then I can actually use this equation to find sine theta, and from these two, either one, I will be able to calculate what is really the lambda for the, for that light. This is one of the most important, I will say, experiment in physics where we use it to calculate lambda. For example, if we look here, we have, suppose you pass light from a helium neon laser. It's a common practice to use laser because it will not diverge through two slits separated by 0.0100 millimeter, and find that the third bright line on the screen is formed at an angle of 10.950 relative to the incident beam. What is the wavelength of the light? Now here I want to bring to your attention something that is really important. Like I have, this one is the central, and then I'm gonna have the first, the second, the third, the fourth, and here 1, 2, 3, 4. This one is m equals 0. This one is m equals 1. This is m equals 2. This is m equals 3. This is m equals 4. And this is m minus 1. This is minus 2. This is minus 3, and go on. This is for the dark, for the bright. For the dark, this is m equals 1, this is m equals 2, then this is m equals 3, this is m equals 0, and that one is 1, and that one is 2. Therefore, if it's gonna say the third, let's say dark, m for it is 2, it's not 3. Okay, then this is really okay, and we know that here d sine theta for the dark is going to be m plus 1/2 times lambda, and m starts from 0, right? Then this is just to let you know. For the, I will say for the light, for the bright, it's not going to be a problem. D here is 0.0100 millimeter, and the angle is 10.95, and the third bright, it is m equals 3, and we want to find lambda. Then I can say d sine theta equals m lambda, and lambda, it is d sine theta divided by m. Here, that one should be converted into meters, sine the angle divided by 3, and that really the light that having and a wavelength that is 633 nanometers. Here, interference patterns do not have infinite number of lines, since there is a limit to how big m can be. What is the highest order constructive interference possible with the system described in the previous on the in the preceding example. It's the same one, and therefore here I can calculate because the maximum angle here that we should have is going to be 90. Because remember, the angle is measured from here, 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 then the maximum is gonna make is 90, and therefore I can say d sine 90 divided by lambda. I know that this is the, you know, the wavelength that was calculated. Then the highest number of m can be 15. Now we are going to talk about multiple slit diffraction. And here, what we use a small piece like this made of glass or made up of plastic. It has so many grooves, even you will not be able to see them. This is, we call it diffraction grating, and that one actually it has like, you can have 3,000 in 1 millimeter or like 500, and it's it's so many. And here when we have that diffraction grating, we're gonna find that the light is gonna be diffracted in a pattern that is gonna be similar to double slit with bright fringes, or they're gonna be on the same, like on both sides. And here, if the light is white, you're gonna see that you're gonna have the rainbow colors as well. Now here, showing you that this is really, the butterflies. This is really the reflectors that we have on the butterfly wings, and they're gonna cause these colors. This is the double slit, and that one here, it is the interference effect. And then here we're gonna find that it is when we have like when we have diffraction imposed, this is gonna happen. Now, diffraction grating with 10,000 lines per centimeter are readily available. Suppose that you have one and you send a beam of white light through it to a screen that is 2 meters away. Find the angles for the first order diffraction of the shortest and longest wavelength of visible light, which is 380 nanometers and 760. What is the distance between the ends of the rainbow of visible light produced on the screen for the first order interference? Now, okay, we need to know here that first there is a very important thing to do, which is we need to calculate what is really the D value. D value is going to be the distance, okay, here, which is centimeter, divided by 10,000. All right, I need to convert this into meters, and that is going to be -6. I know that d sine theta for this is V stands for violet, because this is the shortest wavelength, and we're going to do for the fringe number 1, m equals 1. Then d sine theta for violet equals lambda violet, and then I can find sine for violet to be 49.5. This one here on your calculator, after you calculate this number 0.38, you're gonna have second function and then sine, and then you're gonna put the number, and then you're gonna get how many degrees. We can repeat the same calculation for the red light using the other wavelength, which is the 760, and from that we're gonna get 449.5. Now, for calculating the distance, okay, we can first use that equation here to calculate what is y for the purple or for the violet. And using the angle times 2, which is the screen distance, we will be able to calculate that this one is 0.815, and for the red is going to be 2.338, and therefore just subtract, you're going to find that it is 1.52. Now, this is really here for the single slit diffraction. We're going to have a very sharp, high intensity peak, and the intensity is going to decrease very rapid when we move from the central fringe. Now, here we use uppercase D for the width of the slit. This slit is a single slit, it's just one. And we are going to look for the destructive interference, and we have D sine theta equals M lambda, and here M is going to be plus or minus 1 or plus or minus 2, plus or minus 3. We will not have the 0. Let's solve this one. Example, visible light of wavelength 550 nanometers falls on a single slit and produces its second diffraction minimum at an angle of 45 relative to the incident direction of light. What is the width of the slit, and at what angle is the first minimum it produced? Let's summarize here the values. Lambda is 550, M is 2, theta is 45, and D sine theta equals M lambda, and that is going to be D equals 2 times 550, 10 to the negative 9 meters divided by sine 45, and that is going to give us 1.56, 10 to the negative 6 meters. For B, D sine theta equals M lambda, and M equals 1. Then sine theta equals M lambda over D, and then 1 times 550 times 10 to the negative 9 meters divided by 1.56 10 to the negative 6 is going to give us 0.354. On your calculator, you're going to put sine inverse of 0.354, and that is going to give you 20.7. Okay, I'm going to do another video. Thank you.